6.5 gigatons. That is roughly how much cement China poured in just 3 years, between 2011 and 2013. To put that in perspective, it is more than the United States used across the entire 20th century. Every skyscraper, every mile of interstate, every dam, all of it packed into a window barely longer than a single presidential term. That one statistic tells you almost everything about why the material we are talking about today has quietly become one of the biggest climate problems on the planet, and why a discovery coming out of Chinese laboratories right now has engineers around the world genuinely rattled. The material is concrete. And I know concrete does not sound exciting. It is gray. It is everywhere. It is the last thing most people would ever describe as cutting edge. But concrete is the second most used substance on the entire planet. The only thing humanity consumes more of is water. Not oil, not steel, not timber. Water first, and then concrete, and nothing else even close. Every building you have stepped inside, every bridge you have driven over, every sidewalk under your feet is almost certainly made of the stuff. And here's the part that rarely gets talked about. Making it is an environmental disaster hiding in plain sight. Cement, which is just the binder that holds concrete together, is on its own responsible for somewhere between 7 and 8% of all the carbon dioxide humanity emits every single year. If the cement industry were a country, it would rank as the 3rd or 4th largest emitter on Earth, ahead of entire industrialized nations. That is a bigger climate footprint than all the world's aircraft combined. So when a team of researchers found a way to make concrete dramatically stronger while cutting the cement needed to produce it, and did it without adding a single new ingredient, that is a story worth understanding properly. If you like watching how quiet technical breakthroughs end up reshaping the world, hit like and subscribe so the next one reaches you. Let me show you how it works. Start with the chemistry, because the chemistry is the whole trap. To make cement, you have to take limestone and roast it in a kiln at temperatures well above 1400 degrees Celsius. At that heat, the limestone breaks apart, and here is the crucial thing: it releases carbon dioxide directly as a chemical reaction, not as a side effect of the fuel. This is the detail that makes cement so stubborn. More than half of its emissions are not about dirty energy at all. Even if you powered every kiln on Earth with perfectly clean electricity, the limestone itself would still pump out an enormous quantity of carbon the moment it decomposes. The emissions are baked into the recipe, quite literally. That is why, for decades, this problem resisted every solution people threw at it, and it was not for lack of trying. Engineers swapped part of the cement for industrial leftovers like fly ash and blast furnace slag. Chemists built geopolymer concretes on entirely different binders. Companies experimented with capturing carbon straight out of the smokestack. All of it helped a little around the edges. None of it changed the fundamental math enough to matter globally, because concrete is genuinely one of the most brilliant materials ever invented. And improving something that good is brutally difficult. Think about what concrete actually does. It is cheap enough that the poorest countries can build with it at scale. It is strong enough to hold up a 100-story tower. You can pour it into any shape imaginable. It hardens on its own. It does not rust like steel, rot like wood, or shatter like glass. And it lasts for decades with almost no upkeep. For nearly all of human history, no other material offered that entire package at once. So the core routine, mix it, pour it, and wait for it to cure, has stayed essentially unchanged for generations. And that is exactly where a group of researchers asked a question that turned out to be surprisingly powerful. What if the problem was not the recipe going into the concrete, but what you do to it in the seconds right after it leaves the mixer? Here is something most people picture wrong. Fresh concrete is not solid. The instant it comes out of the mixer, it is a thick, wet slurry, loaded with water, trapped air bubbles, and grains of cement and stone drifting around in a loose, disorganized mess. The normal method is passive. You pour it into a mold, maybe run a vibrating tool through it to shake some air loose, and then you wait. Gravity settles the heavy bits, the excess water slowly bleeds out, and the mass stiffens into shape. That is how it has always been done. The new approach throws that out. Instead of waiting on gravity, researchers apply real mechanical pressure to the wet mix while it is still soft. squeezing it hard from the outside in the range of 15 megapascals, the kind of force you would find inside an industrial press, and that pressure transforms the material from the inside out. The particles get forced together so tightly that the surplus water and trapped air have nowhere left to hide, and they get pushed out. The concrete becomes dense almost instantly, the difference being something like comparing a loose scoop of sand to a pressed solid brick. This technique has a name. Researchers call it compression casting concrete, or CCC, and it has become a genuine global research hotspot. It is not just Chinese teams. Scholars in Australia, Pakistan, France, the UK, India, and Italy have all published on it, but Chinese institutions are very much leading the charge, and the results coming out of the labs are striking. Here is why squeezing out those voids matters so much. Those tiny gaps are where nearly every concrete failure begins. Cracks start at voids. Water seeps in through voids. Road salt and the chemicals in seawater travel through voids to reach the steel reinforcement buried inside, where they trigger corrosion that eats a structure apart from within. Freeze and thaw damage happens when water trapped in a void turns to ice and expands. Shrink the voids and you knock out most of concrete's long-term weaknesses in a single move. The measured numbers back this up. In studies on desert sand concrete, a notoriously weak material, compression casting increased compressive strength by as much as 93% and cut porosity and water absorption by well over a third. In other layered compression studies, strength gains around 100% were recorded. One compaction study pushed the strength improvement even higher, past 180%. The exact figure shifts depending on the mix and the pressure applied, but the direction is always the same, and it is dramatic. And critically, the biggest improvement often shows up in the weakest part of the whole material, the microscopic zone where the cement paste wraps around each stone. In ordinary concrete, that boundary is the flimsiest link in the chain, the first place a crack appears under stress. Under compression, it tightens up hard, and the weakest link becomes far stronger. Now here is the part that makes engineers lean forward. All of this happens without adding anything new to the mix. No expensive additives, no exotic materials, same ingredients, handled differently. And because the material ends up so much stronger, you can actually get away with using less cement to hit the same strength target. That is the whole climate payoff. A life cycle analysis of the technology found that using compression casting in concrete production can cut its carbon footprint by anywhere from 21 to 45% compared with the conventional casting method. That is not a rounding error. That is a serious dent in the emissions of the single most carbon-heavy ingredient in the built world. Now, while researchers were reinventing how concrete gets made, a completely separate Chinese effort was asking a different question altogether: whether some buildings even need much concrete in the first place. This is where a company called Broad Group comes in. If the name rings a bell, it is because Broad has spent years doing things in construction that most people flatly assume are impossible. Back in 2011, one of their teams stacked up a 30-story building in just 15 days. 3 years later, a 57-story tower went up in 19. Those time-lapse videos went viral for a reason. They looked fake, and they were completely real. Broad's newer bet is a material they call B-Core. And it is clever. Picture two thin skins of stainless steel held apart by a dense array of thin-walled stainless steel tubes, all fused together into a sandwich. The whole thing looks a bit like the inside of a waffle iron, except the tubes are brazed to the plates in a special kiln at around 1100 degrees Celsius using a copper bonding process. The design is lifted straight from aerospace thinking, the same logic that lets a spacecraft panel or an aircraft fuselage be both feather-light and enormously strong. Broad itself says the mechanical performance is equivalent to the honeycomb panels used on spacecraft. The point of all that engineering is to do more with far less material. Instead of relying on sheer mass to carry a load, B-Core distributes stress through its structured lattice. The steel skins handle the pulling and pushing forces, the internal tubes handle bending and twisting, and the result is a panel that weighs a small fraction of a comparable reinforced concrete slab while carrying serious structural loads. Because the pieces are prefabricated in a factory and assembled on site, a building goes up fast, clean, and quiet, with almost none of the dust, noise, and waste of a normal concrete pour. And Broad makes a strong durability claim to arguing that stainless steel delivers a far longer service life than conventional building materials and that the whole panel can eventually be recycled. There's one more advantage that matters enormously in large parts of the world: earthquakes. Traditional concrete structures are heavy, and heavy things generate huge forces when the ground starts shaking. A lighter structure has less mass to throw around, so it can absorb and redirect seismic energy differently. Broad specifically highlights earthquake resistance as one of B-Cor's core strengths, and in regions where seismic risk is a daily fact of life, and that includes some of the most densely populated cities on Earth, that is not a minor perk. It is a genuine safety argument. So step back and look at the two ideas side by side. One makes the concrete that does get poured far stronger and considerably greener. The other cuts down how much concrete a building needs at all. They attack the same problem from opposite ends, and together they point toward a future where the built environment carries a much lighter carbon load than it does today. Now, I want to be straight with you about something, because accuracy matters on this channel more than a good story does. There are versions of this concrete story floating around online that come loaded with very specific claims, exact export tonnages, named licensing deals between global cement giants and Chinese firms, precise counts of international patents, monitored bridge decks with exact strength readings. When I went looking to verify those specific downstream claims, I could not confirm them in reliable sources, so I have deliberately left them out. What I have shown you, the chemistry, the compression casting research, the measured strength and carbon numbers, the B-Cor material, and Broad's construction record, all of that is real and documented. The rest I am not going to repeat just because it makes the story sound bigger. You deserve the version that holds up. And here's the honest picture of where this actually stands. Compression casting is real, and the results are genuinely impressive, but turning a laboratory technique into a global standard is a long road. The process needs specialized equipment that most concrete plants simply do not own today. Retrofitting existing facilities or building new ones takes real capital, and while that investment might pay off quickly for a large, well-funded contractor in a wealthy country, the barrier is much steeper for smaller builders in developing economies, which is a real problem, because those are often exactly the places that most need affordable, lower-carbon construction. On top of that, building codes move slowly by design, because getting a structural material wrong is not measured in lost profit, it is measured in lives. Every country that wants to adopt this at scale has to run its own testing, build its own approvals, and train its own workforce. None of that changes what the science shows. It just marks the distance between what is technically possible and what will actually happen out in the world. And closing that distance is as much a question of policy, money, and coordination as it is a question of engineering. But here is what is not in doubt. For the first time in a very long stretch, the basic process of making and using concrete is genuinely changing, not just at the margins, not just on a lab bench, but in a way that could eventually reach the real structures that real people live and work inside. When you are talking about the second most used substance on the entire planet, second only to water, even a modest change to how it gets made does not stay small for long. A 20 to 45% cut in the carbon footprint of concrete applied across the volume the world actually pours would be one of the largest single climate wins available to us anywhere. If this changed how you think about something you walk on and live inside every single day, do me a favor and give the video a like. Subscribe for more stories about the technologies quietly reshaping the world, and turn on notifications so you never miss one. And I want to hear from you in the comments. Compression casting was sitting right there, a change to a single step in a process we have used for over a century, and it took until now for anyone to seriously chase it. So what other obvious breakthrough do you think is hiding in plain sight right now, just waiting for someone to notice?